For decades, behavioral psychology operated on an intuitive assumption about human willpower, the limited strength model. The premise is that self-control functions like a physiological resource. Every time you resist a temptation or suppress an emotion, you use up some of this finite energy until the reserve drains away and leaves you susceptible to failure. To test this in the laboratory, researchers developed the sequential task paradigm. Subjects are forced to complete a grueling initial task, like suppressing their emotions while watching a disturbing video. Then they are given a secondary task that also requires self-control, like solving a difficult puzzle. The drop in performance on the second task is measured as the depletion effect. By 2010, the scientific community had produced a massive volume of research using this method. A team led by Martin Hager aggregated 198 published experiments into a single meta-analysis and condensed them into an overall effect size of D equals 0.62. Cohen's d is a metric used to describe the standardized difference between two groups. A score of 0.62 represents a medium to large magnitude. It suggests a highly robust, easily observable phenomenon. Based on this data, researchers began attributing an immense variety of real-world behaviors to depleted self-control. Everything from succumbing to addiction, to instances of severe violence, to poor academic achievement, were framed as symptoms of an exhausted cognitive resource. Backed by gold-standard meta-analytic evidence drawn from hundreds of peer-reviewed experiments, eco-depletion was considered a proven behavioral reality. 5 years later, a research team led by Evan Carter published a strict methodological audit of the original 2010 data, applying cutting-edge statistical techniques to reevaluate the evidence. Carter's team reached a stark conclusion. Once they accounted for unrepresentative sampling and the quality of the experimental designs, the depletion effect became entirely indistinguishable from zero. Both teams analyzed the exact same scientific literature. One concluded that ego depletion was a powerful, robust driver of human behavior. The other concluded that it did not exist. How could hundreds of peer-reviewed experiments and a major meta-analysis mathematically conjure a behavioral effect out of thin air? The first problem Carter identified was how the original data was gathered. They established strict inclusion criteria to filter out experiments that used unvalidated measurements of self-control. They also removed extension experiments, which were studies that simply assumed the depletion effect was real and tried to apply it to unrelated phenomena, like anxiety about death. This curation process aggressively pared down the literature. A raw list of 620 instances of the sequential task paradigm was reduced to just 116 rigorous, independent tests. These were then grouped by outcome into 8 validated categories, like food consumption, standardized tests, and working memory. With a clean dataset, Carter's team ran a baseline test. They applied a standard random effects meta-analysis, the exact same mathematical tool used in the 2010 paper, to see what the refined data would produce. This table shows the results of that baseline test. Even after the strict filtering, 6 out of the 8 task categories still showed a positive, statistically significant depletion effect. If you stopped the analysis here, the limited strength model appears to hold up. But the analysis requires us to look at the I-squared statistic. I-squared is a metric that indicates the percentage of variation across the studies that is due to genuine differences between them, rather than just random sampling error. The I-squared values here are incredibly high, ranging from 43% to over 88%. In statistical terms, this indicates moderate to substantial statistical heterogeneity. Substantial heterogeneity means that these 116 experiments are not actually measuring a single uniform effect. The data points are wildly scattered by external methodological variables that the baseline calculation cannot account for. A standard random effects model is mathematically blind to this problem. It dutifully calculates an average effect size, but it is averaging data that is severely distorted. This is a series of contour-enhanced funnel plots, a diagnostic tool used to investigate that heterogeneity. We are going to focus specifically on the impossible puzzles and Stroop task panels. On these plots, the x-axis represents the calculated effect size, which we measure as Hedges G. The y-axis represents the standard error, which is an inverted measure of sample size. The largest, most precise studies sit at the top, and the smaller studies fan out toward the bottom. In a healthy scientific literature, the data points should form a symmetrical, inverted funnel shape, centered perfectly around the true underlying effect. Notice the color-filled circles on the graph. These represent published experiments. Instead of a symmetrical distribution, they unnaturally hug the rightmost edge of the blue-shaded contour. That boundary line is the threshold for statistical significance. Now look at the white-filled circles. These represent the unpublished data that Carter's team spent months tracking down by directly contacting the original researchers. The unpublished data falls almost exclusively inside the unshaded region. These are null results. They found no evidence of ego depletion, and as a result, they were never published in peer-reviewed journals. This stark visual asymmetry is the undeniable fingerprint of small study effects and severe publication bias. Because standard meta-analyses average only the observed, published data, they inherently overestimate the true effect. They calculate a mean that ignores the massive file drawer of unpublished, counterfactual reality. Identifying publication bias visually is one thing, but to find the truth, we need an algorithmic correction. We need a statistical tool capable of calculating what the effect size would be if the unobserved data were actually included. To do this, the researchers utilized a method called weighted least squares meta-regression, relying specifically on estimators known as PET and Ps. This animation shows how the funnel plot asymmetry test actually works. We take the skewed data points and draw a regression line directly through them. This line maps a monotonic relationship. As the standard error increases, meaning the studies get smaller and less precise, the reported effect size artificially inflates. The PET and Ps methods follow this regression line all the way backward to the y-intercept. That intercept is the theoretical point where standard error is 0. By isolating the point of infinite precision, the mathematical influence of publication bias is neutralized. These methods do not randomly guess at missing data. They use the specific, measurable trajectory of the bias itself to calculate the true underlying effect. When Carter's team applied the Ps meta-regression to the 8 outcome categories of the ego depletion dataset, the math finally stabilized. This chart compares the initial random effects estimates with the corrected Ps values. The impressive 0.62 effect size from the 2010 literature entirely collapses. Look at the task categories for hand grip, Stroop, and working memory. Once corrected for small study effects, their estimates drop completely into statistical non-significance. They hit 0. The single exception was the standardized test category, which retained a positive effect. However, the regression model proved this was mathematically driven by a single extreme outlier with a tiny sample size, rather than a robust, repeatable phenomenon. When mathematically stripped of publication bias, the idea that self-control acts as a limited physiological resource vaporizes into a statistical ghost. This leaves a final forensic question. What environmental condition allowed such massive statistical variance to take hold of the scientific literature in the first place? This histogram of sample sizes reveals the root cause: chronically underpowered experimental design. The median sample size was a mere 48 participants. Testing subtle behaviors on tiny groups drastically lowers statistical power and widens the margin for error. This low baseline power, combined with a publication ecosystem that actively rewards extreme, statistically significant anomalies, the result was a self-sustaining feedback loop of false positives. 2 decades of literature on ego depletion did not prove that self-control is limited. It proved that without rigorous meta-regression and access to unpublished data, even our highest standards of evidence will reflect our own biases back at us.